This lesson we'll be looking at rates of change. Now we've already seen that when we go through the process of differentiation, we can use that to tackle different kinds of problems that involve rates of change, and this lesson will just be a continuation of that. So let's jump straight into this question here. For the function with the rule f of x equals x squared plus 2x, find the average rate of change for x from 2 to 3, the average rate of change for the interval 2 to 2 plus h, and then the instantaneous rate of change. Now I've got a graph of this function here, f of x equals x squared plus 2x, just to help you visually with what we're doing. If we're trying to calculate the average rate of change for part A for x equals 2 to x equals 3, I've marked x equals 2 and x equals 3, those points on the graph here. We're just trying to find the gradient of the chord, so the straight line that would connect those two points there. So the way we'd go about that is simply through the change in y over the change in x, or the rise over the run. So with part A, we'll get the average rate of change equals the change in y will be the value of the function at x equals 3 minus the value of the function at x equals 2. And the change in x will just be 3 minus 2. Now if we work through that, when x equals 3 in our function, we'll get 9 plus 6 minus, when x equals 2, we'll get 4 plus 4 all over 1. So we're left with 15 minus 8, which equals 7. So the average rate of change from x equals 2 to x equals 3 here is 7. Let's have a look at part B. Now part B is asking us to find the average rate of change for the interval 2 to 2 plus h. So this is our 2 coordinate here, and then the 2 plus h you can imagine will be somewhere out here, or it could actually be this direction if h happened to be negative, but the process is exactly the same. So the average rate of change will be the change in y over the change in x, which will just be the value of the function at 2 plus h minus the value of the function at 2 over the change in x, which will be 2 plus h minus 2. So we're left with, if we come back to our function, which was x squared plus 2x, so wherever we see an x in the function, just substitute in 2 plus h, so we'll get 2 plus h squared plus 2 plus h. Then we subtract the value of the function at x equals 2, so that'll just be 8 if we do that quickly, because 2 squared is 4 plus 2 times 2 will give us 4, so let's just subtract that 8 there, over 2 plus h minus 2 will just leave us with h. So if we expand this out, we'll get 4 plus 4h plus h squared. Expand this next component out, we'll get plus 4 plus 2h minus 8 over h. If we tidy all this up, we will end up with 4 plus 4 will give us 8 minus 8, so those will just cancel out. 4h plus 2h will give us 6h, and we've got that h squared, so it will be 6h plus h squared all over h. We can cancel out those h's, which will just leave us with 6 plus h. So in other words, the rate of change from x equals 2 to x equals 2 plus h, and we don't know that value of h, but we can generalize it to find that the rate of change is 6 plus h. Alrighty, let's have a look at part C here. Part C says, Find the instantaneous rate of change of f with respect to x when x equals 2. Now, this question is slightly different to the others. The others were asking for the average rate of change. This is asking for the instantaneous rate of change. So in other words, we're trying to find the exact rate of change at this point here where x equals 2. And the way we go about finding the instantaneous rate of change is we find the derivative. So for our function, we've got f of x equals x squared plus 2x. If we want to find the instantaneous rate of change at x equals 2, firstly we'll find the derivative. F dash x will give us 2x plus 2. The instantaneous rate of change at x equals 2, so when x equals 2, f dash 2 will give us 2 times 2, which is 4, plus 2, which will be 6. So, in other words, we're saying that the exact rate of change, the instantaneous rate of change at this point where x equals 2 is equal to 6. So it's quite close to the value that we found in part A of 7, which gave us the average rate of change between 2 and 3, but at the point 2, that instantaneous rate of change is 6. Alrighty, let's have a look at one last question. A balloon develops a microscopic leak and gradually decreases in volume. Its volume V at time t seconds is given by that rule. So, question 2. Find the rate of change of volume after 10 seconds and 20 seconds. Now, you need to be careful here because you may be thinking, alright, we've got t equals 10 and we've got t equals 20. I'll simply substitute those t values into our rule here. But that's not going to give us the rate of change of volume. If we substituted those values straight in, that would give us the actual volume at t equals 10 seconds and t equals 20 seconds. It would give us the actual volume of the balloon. We're trying to find the rate of change, so that should straight away signal to you that we need to find the derivative for this question. So we've got V equals 600 minus 10t minus 1 over 100 t squared. If we want to take the derivative of that, we're going to take the derivative of v with respect to t, so dv dt. The constant will become nothing. Minus 10t will just become minus 10. And this 2 comes down to give us minus 2 over 100 t. And we can simplify that 2 over 100 to minus 10 minus 1 over 100, 1 over 50 t, or just t over 50, because 2 over 100 is 1 over 50. Alrighty, now with this, for part I, we're asked to find the rate of change at 10 seconds, so when t equals 10. So we substitute that into our derivative. T equals 10, dv dt will equal minus 10 over 50, which equals minus 10 minus 1 over 5, just to tidy that fraction up a little bit, which will give us minus 10 and a fifth. When t equals 20, which was part B there, part 2, when t equals 20, we'll get dv dt equals minus 10 minus 20 over 50, which equals minus 10 minus 2 over 5, which we can write as minus 10 and 2/5. Now, it's important to add in to these responses we've got here the units we're dealing with. we're told volume is centimeters cubed and T is in seconds. So this rate is in centimeters cubed per second. Centimeters cubed per second. And this one here, centimeters cubed per second. So hopefully that's been a helpful reminder for you of some rates of change problems using differentiation.